as we know that the angle of deviation in a prism depends upon what, that if I write the formula, delta is equals to I1 plus I2 minus A. Okay, so let me draw the diagram. Suppose this is a prism, is the incident ray, first refraction happening like this, and then the emergent ray. So this is the second refraction. So if we draw the normal here and here, so I1 is the angle of incidence, I1, this is R1, this is R2, and this is the emergent ray which I have taken to be I2. So, and this is the angle of prism, which is A. So we have derived in the last lecture that delta is equals to I1 plus I2 minus A. What is delta? Delta is the angle of deviation. What is the angle of deviation? So this was the initial path through which the incident ray was supposed to go, but eventually it has gone in this way. It has gone in this way. So this angle is the angle of deviation. This delta is the angle of deviation. So delta depends upon I1, I2 and A. Basically you can control I2 by changing I1. So what can I comment here? Delta depends on I1, the angle of incidence, and the angle of prism, because I2 can be changed by changing I1 itself. So let us perform, or if we perform an experiment where keeping the incident ray fixed, if you keep this incident ray fixed and if you move the move the prism like this, so I1 is supposed to change. So without changing the incident ray, if we shift the position of the prism and take certain experimental data with different I1, with different incidence angle of incidence, we see that the angle of deviation actually first decreases. Let us draw a graph of delta versus I. Suppose this is the delta presented along y-axis, and this is I presented along x-axis. So if you take a data and plot a graph d for delta versus I, then we shall see that with increasing angle of incidence, the angle of deviation delta first decreases and it reaches to a minimum value, then it increases like this. So basically we can see that for every value of delta there are two angles of incidence. Suppose I am taking this value, I am taking this value of delta. So for this value of delta, we are finding here is one angle of incidence and the other angle of incidence is this. So if this is I1 and this is I2, so for this two different angles of incidence I1 and I2, I am getting the same angle of deviation delta, as you can see from the graph. It is very much evident. Okay, but at this point, we can see that the value of I1 and I2 for this particular point only, value of I1 and I2 become the same. And if I consider that this value is I0, so for this delta, which is the minimum delta minimum, so for this delta minimum, we are having, for delta is equals to delta minimum, we are having I1 equals to I2 equals to I0. Let us say at this value this equals to I0. So thus at this position, the incident ray and the emergent ray are symmetrical with respect to the refracting faces. As you can see, this I1 and I2 will be same. That means this ray is making the same angle with the refracting surface, with the refracting surface this, and this emergent ray is making the same angle with the refracting surface this. So we can see that at this position, at this delta minimum position, at this position, the incident ray and emergent ray are symmetrical with respect to the refracting surfaces. That is all. So at minimum deviation position, I can see that at minimum, this is called the minimum deviation position. Delta is equals to delta minimum, where I1 is equals to I2 is equals to I0. Okay. So basically what is happening here? What can I write here? That at delta is equals to delta minimum, which is the at minimum deviation position, I1 is equals to I2 is equals to I0, and say, and symmetrically R1 is equals to R2 is equals to R0, say. Okay, so now A is equals to what? We established in the last lecture that A is equals to R1 plus R2. So that is equals to twice R0. Okay, so R0 is equals to A by 2. Clear? So delta M, which is supposed to be I1 plus I2 minus A, that is I0 plus I0 minus A, that should be 2I0 minus A. Okay, so as you can see that 2I0 equals to A plus delta M. So I0 equals to A plus delta M divided by 2. So this is an equation which you should remember for the minimum deviation position. The angle of incidence is this, and the angle of incidence, the angle of emergence. Okay, so now if mu be the refractive index of the material of the prism, from Snell's law, what can I write? If I consider air, suppose this, the medium outside the prism is air, what can I write? I can write that mu is equals to sine I upon sine R. So sine I is having the value of this I0. Okay, so that is equal to sine A plus delta M divided by 2, and sine R is having the value of R0, which is A by 2. So let us put sine R0 here. So sine A by 2. Okay, so this is called, this mu equals to sine A plus delta M divided by 2 divided by sine A by 2. So this is a very important formula which is called the Prism formula. Okay, we have studied lens formula, we have studied mirror formula. Now this is what which is called Prism formula. Okay, so we have reached this method in a certain way, and also there is an analytical method through which you can also prove the same thing. So let us explore the analytical method. So what does it say? It says that we know delta equals to I1 plus I2 minus A. So can I write here that delta root delta I1 square plus root over delta I2 square minus A. Okay, so if I write that delta equals to root I1 square plus root I2 square minus 2 root over I1 I2. To nullify this, 2 root I1 I2 minus a. Okay, so this delta becomes root I1 minus root I2 whole square plus 2 root I1 plus 2 I1 I2 minus a. Okay, so where, let us look at the formula here, the expression first. If I look at this equation, look at the right hand side of this equation, look at this expression. So this is having a value, we can clearly tell that if delta to be the minimum, okay, so delta will be minimum if root I1 minus root I2 becomes 0, because if this becomes 0, if this becomes 0, okay, if this becomes 0, then delta will be minimum, because there is no chance that that will be becoming 0. Okay, so that if this is root I1 minus I2 whole square becomes 0, so root I1 minus I2 will be also 0. So you can see that I1 is equals to I2. Clear? So thus at minimum deviation of the prism, which is delta is equals to delta minimum, the angle of deviation is equal to the angle of emergence. Okay, now this deviation is maximum. Where will the deviation be maximum? Delta will be maximum when I1 will be equals to 90 degree. I1 is equals to 90 degree. Okay, that is delta max should be 90 degree plus I2 minus a. Clear? That is not that much important, just understand it. Clear? Now this was a common discussion regarding any kind of prism. Now let us consider a special case, that refraction through thin prism. If the prism is thin, okay, so a thin prism, I'll be considering two special cases here. One is for thin prism, and the second consideration will be for normal or near normal incidence. Near normal incidence cases. For near normal incident rays, I am considering two considerations here. For thin prism, what will happen? The prism will be thinner. That means this A value will be smaller. So for thin prism, it implies that the prism is having very small A value. Clear? Or you can say that the refracting angle of the prism is very small. Now, for near normal incidence, what happens? I is very small. If I is very small, eventually R will be very small. Okay, so mu should be written as sin I1 by sin R1. For smaller angles, you know that sin I1 is almost equal to I1 and sin R1 is almost equals to R1. So we can write I1 as mu R1. Okay. Similarly, if you consider the refraction, I have considered the refraction at this phase for this equation. Now if you consider the refraction at this phase, we can write mu is equals to what? Mu is equals to sin I2 divided by sin R2. So that is also equal to I2 divided by R2 for the smaller values of I2 and R2. So I can write here I2 is equals to mu R2. So now we have two values, I1 is equals to mu R1 and I2 is equals to mu R2. So what was the value of delta? Delta is equals to I1 plus I2 minus A. Okay, so let us write it here that mu into R1 plus R2 minus A. Now you know what? We know that A is equals to R1 plus R2. We have proved that, we have established that while we proved this equation. While proving this equation, we established this fact. Okay, so A is equals to delta is equals to what? Delta is equals to mu into A minus A. So it's equals to, if you take A common, so mu minus 1 into A. So that is the value of delta, the deviation, mu minus 1 into A. So this is the equation you have to remember. Okay, so for near normal incidence, deviation produced by a thin prism is independent of the angle of incidence and is constant for a given thin prism. So it's a very important finding here that delta does not depend on the angle of incidence. Okay, how do I find that? Because delta does not have I1 here. Okay, so remember that for near normal incidences, deviation produced by a thin prism, okay, will be independent of the angle of incidence. Okay, and is constant because mu is constant, A is constant for a given prism. So it is constant for a given thin prism. Okay, so it is a constant value for a given thin prism. So whatever be the value of the angle of incidence, the delta value will not be changing. So this is the all the things we should discuss, we should know about prism. Now one more thing which is left, that the limiting angle of incidence for no emergent ray of prism. So the next thing that I am going to discuss as finding out the limiting angle of incidence, limiting angle of incidence for no emergent ray. Let us understand it very carefully. So if I increase the angle of incidence, sometimes it might happen that there is no incident ray, there is no emergent ray, from this face, from this refracting face of the prism. Can it really happen? Let us find it out. So if I have a prism like this, and if this is the angle of, the incident ray, suppose this is the normal here and this is the normal here, and if the first refracted ray is this, so this is the, suppose this angle is the theta angle, which is the angle of incidence for this refraction. And as we know, if this is having the mu refractive index, let us say this is air and air, or whatever medium it is, if you consider the prism is made up of denser medium than its surrounding, so this refraction here at this surface is happening from denser medium to rarer medium. This is denser and this is rarer. Okay, so if it happens by chance, if it is happens like this, that the angle of incidence at this surface, okay, is greater than the critical angle for the material of the prism, then there would be no emergent ray. This is denser, this is rarer. So it's a typical case. If theta becomes greater than the critical angle for this material of the prism, okay, then there would be no emergent ray. Okay, there will be the total internal reflection will happen here. So in this case, if theta becomes greater than the critical angle, so there will be the total internal reflection in this way. So that will be the angle of reflection, which is theta only. Okay, so for this, say, let us say this is I1, okay, and this is, let us say, R1. So R2 is theta here, which happens to be greater than. Okay, so if R2 equals to theta is greater than the critical angle for the material of the prism, there would be no emergent ray. Clear? So what is happening here? If theta becomes the critical case, sorry, in the limiting case, if you consider the limiting case, in the limiting case means that theta is just equal to the angle of incidence theta is just equal to the critical angle. So in limiting case, what happens? We have already discussed in total internal reflection the sine theta value will be equals to 1 by mu. We discussed that. Now, if we in limiting case, what will happen? In limiting case, this is the thing, and theta, the emergent ray, will be grazing across the this surface. Okay, so if this is the normal, this is the normal, so this is the theta here in this case. In limiting case, this is the limiting case. Okay, the emergent ray will be just passing along AC phase. Clear? So if we consider the Snell's law here in this case, this is I, so let us say this is I, and suppose I1, this is R1, this is theta. Okay, clear? So what is happening here? That sine I1, okay, will be equals to mu sine R1. Clear? Understood? And R1 is what? R1 is, here in this case, here R1 is R1 and R2 is theta. So A is equals to, you know, R1 plus R2. So A is equals to R1 plus theta. Clear? So R1 can be written as A minus theta. So I am replacing this value of R1 here. So that can be written as mu1 sine A minus theta. Clear? So if we expand this, sine I1 equals to mu sine A cos theta minus cos A sine theta. Clear? So let us expand this more, that mu sine A cos theta minus mu sine theta cos A. Now look at this very interesting case. What is the value of mu sine theta? From this, mu sine theta equals to 1. Okay, so that value is equal to 1. So what can I write here? That mu sine A cos theta minus cos A. Okay, so cos theta can be written as mu sine A root over 1 minus sine square theta minus cos A. Okay, so that can be written as mu sine A 1 minus, what is the value of sine theta? 1 by mu. So sine square theta is 1 by mu square. So that will be 1 by mu square root over cos A. Okay, so if you just solve this part and this part, you shall find that this root over 1 minus 1 by mu square will be equal to root over mu square minus 1 divided by mu. So if you multiply mu with this part, mu will cancel out, and that will be mu square minus 1 sine A minus cos A. Okay, so that is the limiting value of, so that is equal to what? That is equals to sine I1. So this I1, this is for the limiting value. We are writing this for limiting value, for limiting value. So for the limiting value of angle of incidence, that I1 should be equals to sine inverse of this part. Sine inverse root over mu square minus 1 sine A minus cos A. So this is the thing we need to understand about prism. That is all for today. Okay, so this is the thing that you should remember, practice. So I hope there is no other thing left. Okay, bye bye.